So we've successfully extracted a wood sample from this tree, and in a perfect world, we would have reached the pith. We'd have an entire intact sample of wood that allows us to start counting the layers of xylem from the pith out to the bark, or you could count from the bark into the pith. Anyway, we have a perfect intact sample of wood. But what happens if you don't have an intact sample of wood? If you were only able to collect a small sample from the interior of the tree? That happens when you have a large diameter tree and a relatively small increment borer. Or it could happen if you hit a pocket of, say, rot or a cavity inside the tree that allows you to only extract a small sample of wood. How do we determine the tree's age in that case? Well, there are ways to deal with that type of error, that type of circumstance, and that's the reason that you take the diameter of the tree at the very end. So even if you have a perfectly good sample of wood, that sample of wood can break between now and the time you get back to the laboratory. So it's always a good idea to collect the diameter of the tree at the very end, and that's what we'll do now. So to collect the diameter of the tree, we can use a measuring tape. If all you have is a regular old measuring tape that's measured off in inches, that's fine. Here I have a DBH tape. And the DBH, again, stands for diameter at breast height, because we're measuring the diameter of the tree at breast or chest height. Again, you'll notice that the DBH tape has two different sides on the tape itself. On one side, you have gradations of tenths of a foot. On the other side, I'm not sure what you call those. They're supposed to be measured off in inches, but those increments look much longer than an inch, don't they? Well, that's what makes this DBH tape so special, is that it's calibrated to allow you to measure the diameter of the tree by placing the tape all the way around the tree itself. What you have here are inches that are multiplied by pi. So 1 inch on this side of the tape is actually equal to 3.14159 inches. So why is that important? Why is that a big deal? Well, I'll show you now. So as a teacher, if all you have is a regular measuring tape, you can certainly measure the circumference of the tree that you are determining the age of. So with the diameter tape, I have a tack that allows me to tack into the tree, and that will hold the tape in place. Then you can work your way around the tree. Join the tape together, and what we have is a tree that is 6.7 feet in circumference. So we've measured the diameter of the tree at 6.7 feet. 6.7 feet is the same as 80.4 inches with the handy old calculator here. So if you refer to geometry, the circumference of a tree is equal to pi times diameter. So if you wanted to find out the diameter of the tree, if all you have is a simple measuring tape, you can take your circumference measurement and divide it by pi in order to get the diameter. So 80.4 inches divided by pi is equal to 25.6 inches. So the diameter of this tree, 25.6 inches. What we want though, we want the radius. So in order to determine the radius of the tree, you have to divide the diameter by 2. So 25.6 divided by 2. We have 12.8 inches. That's the radius of this tree, 12.8 inches. So again, if all you have is a simple measuring tape, that's fine too. That will still allow you to collect the diameter of the tree. So we took the circumference first with our measuring tape, and the circumference was 6.7 feet. 6.7 feet equates to 80.4 inches. If you recall geometry, the circumference of a tree, or circumference of a circle, which is represented by the trunk of our tree, Circumference is equal to pi times diameter. So in order to determine the diameter, you take your circumference and divide that by pi. So I'll have 80.4 inches divided by pi, or divided by 3.14, 159, etc. We get 25.6 inches. That's the diameter. From the diameter, we're going to want the radius. And we'll find out why we want the radius a little bit later when we do our algebraic work. But we have 25.6 inches divided by 2. That's equal to 12.8 inches. So remember, the diameter is 25.6 and the radius of this tree is 12.8 inches. So again, as a forester, what makes the diameter tape so handy is that it's calibrated so that you don't have to do that geometry in the forest. So all you need to do is take the circumference or wind the tape around the trunk of the tree itself, and the number that you're going to arrive at is actually the diameter of the tree, because each of these gradations is multiplied by 3.14. So we'll tack the tape into the tree itself. We'll work our way around the trunk of the tree. And you'll see that the diameter winds up being roughly what we estimated before, over 25 inches in diameter. Again, this comes from geometry, where the circumference of a circle is equal to pi times diameter. If we want to find the diameter, d, we simply need to take circumference divided by pi. Diameter is equal to circumference divided by pi. If we want to determine the radius, r, we simply take the diameter and divide by 2. In our previous example, diameter was 25.6 inches. So our radius would be 25.6 inches divided by 2, or 12.8 inches. So why is it important to determine the radius? Well, as we core into the tree with the increment borer and extract a sample of wood, our hope is that we will reach the pith, that dark central point of the tree. Yet sometimes we may capture only a portion of the tree, as indicated here by the green. In this case, we'll want to measure the length of the sample we did obtain and determine what proportion of the radius this is.